Mama.
Assalamu alaikum. Is my voice clear? Okay, I think that Abdullah has a problem into connection, so we can start our lecture, inshallah. So, welcome everyone. Our webinar entitled Introduction to Field Development Planning. I am Muhammad Amin. I am a senior reservoir engineer in GBC in Egypt. So our agenda will include first, need for a plan. Second, the definition for field development planning. Then we will have examples for field development planning activities, like the evaluation for the field potential. Then we will have practice for a case study for a field that is called Oscar field. Then at the end, we will talk about what if we don't have a plan. So first of all, you should know that everything that into your life, you should have a plan to do it. So if you don't have any plan to do something, so we will have you want to do this thing efficiently, okay, with high efficiency. So as we have into oil and gas business, we will invest a lot of money. So we need a plan to invest this money. We need a plan to invest this money. So something that someone is typing that no voice. So again, is my voice clear or not? Clear, okay. So again, so because we are investing a lot of money into the oil and gas field to produce from it, so we need a plan that optimized according to the amount of money that we will invest into that field. So if you look into the production performance version for any oil field, so you will see that we have initial period, which is the exploration phase. Into that phase, we are drilling more wells to explore the borders for our field, to test the productivity for the reservoir, to see amount of oil, if we did well test, reservoir limit test for that field, to know the borders for the reservoir and the amount of oil and gas that existing into subsurface. So that is the exploration and appraisal stage. The second stage is the development stage. At the development stage, now we have a full understanding for our field. So we will drill more and more wells to develop our to develop our reservoir and to have more oil production. Then after finishing the development and reaching the optimum number of wells, so the production will start to decline. The production will start to decline, and actually that is the end stage of the life of our reservoir. At this stage, we can do some activities like we can do some EUR, we can use new technology, we can revisit the old wells to sidetrack them and so on. Okay, to maintain the production at the end life of the reservoir. At the middle stage, we can also study the possibility to apply water injection or gas injection and any secondary drive mechanisms. So we have 3 stages for the life of the reservoir. We have the first stage, which is exploration and appraisal stage. So the plan for exploration appraisal include basin analysis, depositional environment analysis, structural analysis, seismic studies, exploration drilling, and appraisal wells, and potential estimation, to have estimation depending on all of that information to estimate our the potential for the reservoir. And at the end we will have we also have economic analysis for all the costs that will be invested into the exploration plan. Okay. Then after that, then the next stage, which is development and early exploitation stage, which is the main task for a reservoir engineer to optimize it. So first, the reservoir engineer will propose some activities for development and depletion strategy. Also, we will have a plan for data acquisition and analysis. We will do some modeling studies using or starting from the analytical, very simple methods like the material balance and decline curve analysis and so on, going upward to the sophisticated techniques like numerical simulation and so on. Also, we will have forecasts for the production and the reserves. We will have also optimizing for the facilities, and at all stages, we are committed to economic optimization. So that is the development planning, and that is the main topic that we will talk into our webinar. The end stage for the reservoir, which is the maturity and the pre-abandonment stage. So in that stage, so sorry again, someone some people are saying that no voice. So is there any voice or not? It's clear, I think that. Okay. Okay. So for the last stage for reservoir life, which is the exploitation plan. So into that stage of reservoir, we need to check if we can employ or deploy EUR technologies, use another new technology, another method for using the already drilled wells and so on. And again, we will have economic optimization. At all stages of reservoir development, exploration, and exploitation, we need to have economic optimization. We need to have economic optimization. So again, for the field development planning, we are focusing on some items to be determined, like the well spacing, the number of wells, the recovery schemes. If we will apply water injection or gas injection, what are the optimum gas injection rate? What is the optimum water injection rate? What is the optimum production rate? Because in some cases we have fields that is very near the bubble point. So if we try to produce from this field at the maximum production capacity, that will lead that the reservoir pressure will go down very fast below the bubble point. That will arise some gas production problems that will at the end it will reduce the oil production rate. Okay. But what if we have a field or a reservoir that is very far from the bubble point? The initial reservoir pressure is very far from the bubble point. So for that case, we can produce from this reservoir at the maximum capacity, because we don't have any problems related to the gas production. Okay, but at the other side, you should study the other problems like sand production, like any other production problems related to the wells and related to the reservoir properties. So again, the field development planning is focusing on the middle life of our reservoir, not the initial life, or that not the initial stage, which is exploration and appraisal, and not very focusing on the late life. The late life is called exploitation plan. Some companies are including the late life and the middle life, or the middle stage and the end stage, at the field development plan. Okay, but the correct is that the field development planning is focusing on the middle stage of life of the reservoir. So the first stage or the first step into the field development planning is the data acquisition, because the reservoir engineer can't work without any data. Because if we will assume everything, so we will assume a new reservoir that can very far from the reality or from the actual nature of our reservoir. So we have some data that we are acquired before starting the production, and we have some data that we can acquire after putting on the production. So some data like coring, we can have a core sample, we can have a PVT sample, and we will go, or we will speak about the applications for the PVT data and the core data into the field development planning. And also after putting the field on production, we can also acquire some other data, like we can do well test, we can do production test to see the productivity of that reservoir, because in some cases we may have a huge original oil place, but actually the productivity of the wells is very weak. So in that cases, we can sit into the planning or the development planning activities that we need to have hydraulic fractioning, or we need to have a stimulation for the wells to enhance the productivity, Okay, so the first stage or the first step is the data acquisition and analysis. Examples for that is the BVT data. We have many applications for the BVT data, and actually the BVT data is a corner point for the development activities, like reservoir flow typing. The development activities for heavy oil field is different from the activities that will be done for volatile oil fields. For example, for the facilities, if we have volatile oil well, so we can recommend that we have 2 stages or 3 stages of separation. We may have first separator, second separator, and the stock tank. But for the very heavy oil separator, we can recommend that we don't need any separator. You can go directly to the stock tank, because we don't have very high GUR. We don't have very GUR, but in case of volatile oil reservoir, we may lose a lot of oil into the gas phase if we don't have multi-stage separation into our facilities. Also, for the field potential evaluation, we all know that the equation to calculate the oil in place and the gas in place, including beta O and beta G. If we have error into the beta O or the beta G, so we will have an error into estimation for the original hydrocarbon in place. For the production performance, the production performance for heavy oil well is different from the expected production performance for the volatile oil. The recovery factor for heavy oil is different from volatile oil. The facilities and well lifting methods that can be used for low GOR oil wells are different from the facilities that can be used for high GOR wells. For example, we can use the sucker route. We are using the sucker route pumps for the heavy oil, but on the other side, we may have or we may use the gas lift for high GOR wells. And at the end, what about the flow assurance and the HSE or the safety issues? In case one of that examples, if we have H2S into our field or into our reservoir fluid, so the materials that will be used into the well integrity equipment and the material that will be chosen for the production facilities, it will be different from the case that we don't have H2S. So at the end, all of that issues and all of that problems, it will affect on the cash flow. It will affect on the money, the cost, and the revenue that will be expected from that field. Also, that for the BVT. What about the core? So the core, as logic, our reservoir is composed from two components. First, fluid, then rock. So if you don't have any information about the two components, so you don't have any data about your reservoir. So we should have data, or we should have fluid data, and we should have rock data. So what are the applications for reservoir rock data? First, fishes distribution. And we will see the importance to have the modeling for the fishes distribution and how many companies are drilling many dry wells due to not having fishes distribution model. Also, the production prediction. If we don't have any data about the wettability for your reservoir, the capillary pressure, and the relative permeability, so you can't do any estimation or any prediction for the water production into the future. Also, what about the reservoir oil saturation? Actually, the main or the focus on the late life of our reservoir will be on the residual oil saturation, or the oil that will be remaining into our reservoir after the middle stage of development. So what is the quantity for the reservoir oil saturation? Also, what about the sand control? Many wells can be lost. Many wells can be lost due to no sand control. And the sand control is a function of the geomechanical properties for your reservoir that can be evaluated by integration of core data plus the sonic data and the other log data. So if you don't have such data, so you don't have any control for the sand production. Also, the rock typing and saturation height modeling. if you are dealing with a carbonate reservoir, the carbonate reservoir is usually very heterogeneous, and this heterogeneity will require to have rock typing and saturation height modeling. Good modeling for the rock typing and its distribution into your 3D model, and also the saturation height modeling for calculating of oil in place and the original gas in place. So if no data about the reservoir rock properties, so you don't have very efficient planning for the development of your reservoir. After the data acquisition, so we will use that data to evaluate the potential for our reservoir. The first data or the first information that the management will ask you about the reservoir is about how much oil existing into your reservoir. And the second question, it will be, okay, if we have 100 million oil barrel into subsurface, what is the percentage of that accumulation can be recovered or can be produced? That will be the reserve. So we wanted to evaluate the oil place and we wanted to evaluate the reserve. We have many methods that leveling from its complexity, from the very simple to the very sophisticated, okay, for evaluating the oil in place and the reserve. For the oil in place, the very simple method is the volumetric method. The volumetric equation for the oil in place estimation and the oil gas or the original gas in place. So if we have volumetric estimation for the oil in place, so we can assume recovery factor depending on what? Depending on the expected drive mechanism for your reservoir. For example, if you are having depletion drive mechanism, so we are expecting a recovery factor that is ranging from 10% to 20% or 25%. So that is for depletion. That is for depletion. So what if we have aquifer connected reservoir? So we have additional energy source, which is aquifer. So it will increase the recovery factor. It will increase the recovery factor that can reach to 75%. 75%. Okay, someone will ask now, how we can estimate the recovery factor? If we don't have any other data, how we can know the recovery factor for our... Actually, you can know or you can assume the recovery factor. If you don't have any other data, you can assume it. Depending on that, assuming that the drive mechanism for your field is the same as analogy from other fields. So if we have a field and that is field is surrounding with other fields, so we will ask the other companies, what is the drive mechanism in your reservoir? So they will see that the depletion. So we will assume that we will have also depletion drive mechanism into our reservoir. So we will use the recovery factor for depletion drive mechanism. So that is in case that we are using the volumetric method and only recovery factor, assumed recovery factor. Okay, great. So what if we have more data like the production decline rate? Production decline rate. The data from the analogy fields, or we can also use some correlations that can get the decline, the production decline rate, depending on the permeability, porosity, the connectivity, and also, so we can use that correlation to estimate the decline rate of the production. Okay, great. So we can level up to the second level of accuracy and more sophisticated from just using the volumetric estimation and recovery factor to the decline curve analysis, decline curve analysis. Great. So we will use the decline curve analysis if we have certain number of wells. So every well has a cumulative production. So this is the cumulative production that we can get from this reservoir in number of years. So that's our reserve. Okay, great. So from reserve and the oil in place, we can calculate the recovery factor. Great. So what if we know we need to have higher accuracy? So let's go to simulation. We have two types of simulation. We have the analytical method and we have the numerical method. Analytical method, so we will use the material balance, using the material balance. And actually, the material balance is very useful into some fields, like in case that we have low viscosity and moderate permeability. If so, the material balance will give you accurate results into that case. If you have very high viscosity and we have very low permeability, so the material balance results won't be valid into that case. And you must go to numerical simulation. Okay, so the most accurate method is to use the numerical simulation, but the numerical simulation will have additional cost that can impact the cash flow of your field or your project. So in that case, if you don't need such accuracy of numerical simulation, so you can say that it's enough to use the integration between volumetric method, the decline curve analysis, and the material balance, and it is enough for me, and it's enough for the accuracy that I need for my reservoir. Also, one of the useful methods that we can use to estimate the oil in place, which is well test. A certain type of well test is that is called reservoir limit test. Okay. Okay. So for the volumetric method, as you can see, that is the equation for the gas in place and the equation for the oil in place. Okay. And each equation has certain factors like the porosity, like the net pay, like the beta O, and the water saturation. Great. So again, we have reservoir rock properties and we have fluid properties. Great. So let's assume that we have a certain accumulation, and this accumulation is about 1 million barrels. But at subsurface conditions, we need to have this volume but on surface. So we will use the beta O, or the formation volume factor. So in case that, let's assume that the beta O is 1.01. So if you divide 1 over 1.01, so it will be equal to 1, near to 1. So let's assume that the oil price is $60 per barrel. So that is our revenue. Great, congratulations. But what if your assumption is not correct and the correct value is 1.3 for the beta O? So in that case, that accumulation is equal to 0.77. So your revenue in that case will be $46 million. So you can see the STOIP, or the difference into the beta O. The difference into beta O is almost about 0.3, but the difference is reflected into the STOIP and the revenue to have about difference. The difference is about $13 million, which is very, very big effect on the cash flow of your project. That is the cost of dirty data. If you don't have a data, so it will be a mess for you. So that is the importance to have good data acquisition. Okay, great. So, okay, we drilled many wells into our field, and we need to have evaluation for the oil plays. Okay, great. Let's assume, let's go to that equation, and input average value for the porosity, average value for the net to gross, average value for the area, average value for the water saturation, and the value for the beta O. Great. But actually, we don't do that. We don't do that. We are doing a study that is called uncertainty study. Into the uncertainty study, we will use a range for each property. We will have a range. We will use a range for the porosity. For example, if we drill 10 wells and the minimum porosity was 0.15 and the maximum porosity is 0.22, and also for the net thickness.
You know, it's about you, Yanado. Are you talking about you?
Please mute your microphone. And so for every property, we will have minimum and maximum. We will have a range for each property. Okay. That range for porosity, that range for the net thickness, that range for the water saturation, it will be incorporated into the calculation. We will have many values. We will calculate many values using the range for porosity, the range for each properties, and to have a distribution for the oil in place, Then for the management, we will report not just single value for the oil in place, not just single value for the reserve. We will report at least 3 values: minimum and maximum, and most likely B10 and B50 and B90. Okay, so at this example, as you can see, we have the B90 is 3.3 and the most likely is 5.7, and the maximum or the B10 is 7.9. Okay, we incorporated for the bulk volume, minimum, maximum, and move for every data. Before doing the statistical analysis, we are doing distribution analysis for each property to know its distribution. We have many types of distributions. We have the log distribution. We have the normal Gaussian distribution. We have triangular. We have the uniform, which is having only minimum and maximum, and so on. So we will analyze the data for the porosity, the data for water saturation, the data for the net thickness, and so on, to see the distribution type for each property. Then we will include that data into our simulation or into our estimation for the oil in place. That method is called Monte Carlo simulation. Which is kind of stochastic methods for oil in place estimation. Okay, great. So now we have a series of values for the oil in place. What about the reserve? The reserve, as we mentioned, that we can, if you just have volumetric estimation for the reserve, so the reserve will be equal to the recovery factor multiplied by the oil in place or the gas in place. Or from the DCA or the decline curve analysis or the simulation, it will be the cumulative production at the life end of the reservoir, which is the maximum cumulative production by the economic condition that can be recovered at economic conditions. Okay. For the assumptions for the recovery factor, you can use data for depletion drive, gas cap drive, water drive, and gravity drive. For the DCA, as you can see that we have 3 types for decline, or we have 3 patterns for decline. We have the harmonic, we have the hyperbolic, and we have the exponential. Usually, and into our daily practice for the decline curve analysis, we are using the exponential. We are using the exponential. The exponential is called constant percent decline. Constant percent decline. Okay, we can assume that our production is declining by 10% through 1 year. Okay, or declining by 20% through 1 year, and so on. Okay, usually we are using the exponential. Okay, great. So we have a certain approach that in which we can use the volumetric, we can use the decline curve, and we can use also the simulation. The first step into that workflow is to calculate the original hydrocarbon in place. Okay. Then we will determine the reserve by introducing or assuming a recovery factor. Okay. Then we will use decline, we will do decline curve analysis for a single well. We will assume its initial rate, depending on what? Depending on the data that we will gather about the nearby or from the analogy. Okay. Or if you have just one exploration well, so you already tested that well, so you can estimate its initial rate. Okay. So from the DCA, from the decline curve analysis, you will have the reserve for single well. And from that equation, you will have the total reserve. So if we divide the total reserve per the reserve per single well, so it will equal to the number of wells that you will need to develop that reservoir. Okay, great. But in some cases, the production performance that is coming from the decline curve analysis, is not matching the reservoir pressure performance. So in that case, we will validate by simulation. Or usually we are using the material balance equation, or the numerical simulation. But as a rough estimation, now we have few data, and we need to use that just a few data to have a conceptual model for the development activities for our reservoir. So we will use the the integrated workflow oil in place calculation from the volumetric data, reserve by using assumed recovery factor, decline curve analysis to get the reserve per single well, using or having the number of wells, then validate that by doing the material balance calculations. Okay, to have more complexity, we will go to simulation. But if you usually at the beginning or at the start of development activities, we don't have a big deal of information about our reservoir. So initially, we will have a rough estimation for the development activities. Then we will get more data about our reservoir, so we will increase the complexity of our conceptual model of our reservoir. Okay, great. So actually, the field development activities has two sides. Like a coin, has two sides. The first side, which is the technical or the production side. Number of wells, facilities needed to be installed, number of wells needed to be drilled, a certain production that is expected by the decline curve analysis, and so on. At the other side, which is the economic evaluation. The economic evaluation has very simple equation. the net cash flow is equal to the cash in, the profit from selling the oil and gas, minus the cash out, which is OPEX and CAPEX. The OPEX and CAPEX. Okay, great. So let's have an example. We have a field that is producing just 500 oil barrels per day, and a reservoir engineer proposing that we need to have water injection. Great. So the water injection will have a certain cost. We will have some facilities to be installed for such project of water injection or gas injection. Okay. So we will compare the incremental or the increase of production due to applying of water injection versus the cost of applying the project of water injection. In case that we have a high impact of the cash flow, a high production that can substitute or can have or can cover the cost of the project of water injection, it's okay. And let's go to apply water injection. In the other case, the water injection can increase the production, but the incremental or the increase in the production not cover the cost of water injection. So in that case, we will recommend not to apply water injection. Despite that, the water injection will increase the production. But remember that our main objective, not to produce more, but to get higher net cash, to get higher money, to get or to gain higher money, okay, or to get more profit. So again, our objective, not to produce more, but to get optimized cash flow. Great. So usually we have that it is typical cash flow diagram. So in the first years, on the first period, we have some CAPEX. Okay, we are producing, but we have very high initial CAPEX at the initial period of production. So we will produce until we will reach to a certain point that is called payout time. Then at this payout time, so we will start to have positive cash flow. In that period, all of our production will go to cover the CAPEX, the initial CAPEX, the cost of wells, the cost of the production facilities, and so on. Okay. Then after covering that CAPEX, we will start to have positive cash flow from our production. Okay. Then until reaching to the maturity or the decline period, so the cash flow will decline because our production will start also to decline. Okay. So let's go to have simple application example, okay, to see how we can determine the number of wells and do simple project feasibility or the economic modeling for our project. We have a field that is called Oscar field. We have 100 million oil barrel. We have the drive mechanism is a depletion drive. The recovery factor is about 20%. Assuming annual production decline rate is 15%. The facilitated installation cost is $100 million. Well cost is $5 million per well, and the OPEX is $20 per barrel, and the oil price is $100 per barrel. Okay. We will use just a simple Excel sheet to know the number of wells that will be needed and to do project feasibility study. Okay, how we can do that? We will open Excel sheet. Okay, empty Excel sheet. Then the first tab, we will call it number of wells. Okay, the oil in place is 100 million barrel. Okay, the recovery factor is 20%, and so the total reserve is equal to 100 million oil barrel multiplied by 20%. So we will have 20 million barrel. Okay, that is the total reserve from the reservoir. Okay, for the total field. Okay, great. So now we have the total reserve by using assumed recovery factor and volumetric estimation for the oil in place. Let's do decline curve analysis for one well. Okay, the first column, it will be the months. The second column, it will be the oil rate, the oil production rate, barrel per day. The third column, it will be the amount of oil that will be produced through 1 month, okay, which we will call incremental oil. It will be in unit of million barrel. And the fourth column, it will be the cumulative oil production. It will be also million barrel. It should be million standard oil barrel, okay? Okay, so the first month, let's assume that the initial rate for the well, it will be 1,000 oil barrel per day. So for the incremental, it will be equal to, or the monthly oil production, it will be equal to the oil rate multiplied by 30.4. 30.4 is the average monthly days, which is equal to 365 over 12. Okay, then here it should be by million. Okay, and that is the cumulative oil production at the first month. Then we want to have or to include the decline. So the decline here is about 15%. Okay, so the production rate into the second month, it will be the production rate at the first month multiplied by 1 minus 15 over 12. The decline monthly. Okay, so that is the rate at the second month, and the incremental oil, it will be the same, and the cumulative oil production, it will be equal. The cumulative oil production at the first month plus the incremental oil from the second month. Okay, okay, great. Then we will, let's assume that the minimum oil rate for a well to be 100 oil barrel per day, 100 oil barrel per day. So we will do our decline curve analysis until reaching oil rate about 100 oil barrel per day. Okay. So let's see about 200. So we reached 80. No, we don't need to that. We will stop our decline here. So here, as you can see, that is the cumulative oil production that can be produced by using single well. Okay, great. So the number of wells that will be needed, it will be equal to the total reserve over the cumulative oil production from just single well. So we will need about 9 wells. We will need about 9 wells to develop our reservoir. Okay, great. Let's go to the feasibility study or the economic study. Okay. Again, the first, it is the months. Okay, the first column. Then the cash in. Okay, the cash in, it will be $1 million. Okay, or let's have it into the third column. Here, it will be the production from the 9 wells into million barrel. Okay, then that is the cash in. Okay, we need to have the cash out. Let's remember we have the cash out. It's OPEX plus CAPEX. Okay, so here the OPEX is about $20 per barrel, and the CAPEX is the initial CAPEX is equal to the facilities installation cost, which was about $100 million, and the well cost, the single well will cost $5 million. Okay, so here we will have CAPEX. Okay, CAPEX also into $1 million. Okay, then we will have the cash out. Or let's calculate the OPEX first. OPEX also in $1 million. Okay, and at the end we have cash out. Great. Then we have first month, second month, and third month, and so on. Okay, so the production, let's assume that the 9 wells will start the production at same time. Okay, usually we are conducting the economic study for certain period, for 5 years or for 10 years and so on. So we will do the economic study for 5 years, which is 60 months. So the production, it will be equal to the production of single well multiplied by 9 wells. Okay, the cash in, it will be equal to the production multiplied by the oil price, which was $100. So the production multiplies by $100. The CAPEX was 100 million. The OPEX was $20 per barrel. So the OPEX will be 20 multiplied by the production. So the cash out, it will be equal to the CAPEX plus the OPEX. Then here we will have the column of net cash flow into $1 million. And we have also cumulative net cash flow into million also, $1 million. The net cash flow, it will be equal to the cash in minus the cash out. Okay, the cumulative net cash flow at the first month, it will be equal to the net cash flow. Okay, let's go to the second month. So the second month, it will take the production from here multiplied by 9. The cash in is multiplied by 100. The CAPEX, we don't have any CAPEX. Okay, with the second month, we have only the initial cost for CAPEX at the first month. The OPEX is production multiplied by 20. The cash out, okay, the net cash flow, and the cumulative here, it will be equal to the cumulative at the first month plus the net cash flow at the second month. Okay, let's drag until 65 years. So as you can see that if you plot months for the production versus the cumulative cash flow, let's have that on other axis. So as you can see, the production decline, and we have initially we have negative cash flow. Why? Because we have capex, initially cost for the facilities, initially cost for the wells. Okay, I think that we here into capex we should have also the capex of the 9 wells. So 9 wells multiplied by the cost per well, which was 5 millions. Okay, so we have negative value for the cumulative cash flow due to the initial cost for the facilities and the well drilling cost. Then we will start until reaching to the payout, until reaching to the point at which we recover all the project costs. Okay, at about 7 months, and after about 7 months, then we will start to have positive cash flow. At the end of 5 years, we will have a revenue or a net cash flow of about $782 million. Okay, so this just a simple calculation, calculation for the cash flow and the determination of the number of wells and reserve and so on. Okay, but actually into that rough estimation, but into the practical and into the practice, we should include more complexity to our studies. We should have more complexity into our studies. If you have numerical simulation, it will lead to more accuracy. If you have more data about your reservoir, if you have better estimation for the decline of the production, if you have well test to have productivity for your well and so on, so it will be addition to the accuracy for your estimation. Also for the economic estimation, as you remember, we did uncertainty analysis for the oil in place, but we didn't do that here. Okay, so if we can do uncertainty analysis for the oil in place, uncertainty analysis for the recovery factor, all of that uncertainties will be reflected into uncertainty also into the cumulative cash flow and our economic modeling. Okay. Okay, great. So that was an example for development activities and the economic estimation. Okay, let's have some cases for a companies that didn't have a plan or have a mistakes into data acquisition or planning and so on. We have very important common code into reservoir engineering. If you considered all the design parameters except one parameter, be sure that this parameter will be your nightmare into the future. If you say it's okay, no, it's okay for me and it's enough, we don't need any additional data to have more accuracy and it's enough, be sure that this parameter that you ignored will be your nightmare into the future, your nightmare into the future. Okay, we have a case here for international company, not local company in Egypt. This company discovered a large gas field and they acquired a gas sample or acquired a sample and interpreted that we have a gas condensate reservoir. Congratulations, we have a gas condensate reservoir. So they started to have processing station for the gas condensate field that costed about $2 billion. You can imagine $2 billion. Then after more drilling, they discovered that this wasn't a gas condensate reservoir. It was a volatile oil reservoir. So it was a great loss for this company. Another company which was very big exploration and production company that acquired offshore heavy oil field, then also took some samples that indicated that they may have high viscosity, especially if we may have water production. The water production it will add to complexity because it will lead to have emulsion viscosity. The pipeline design indicated that you should or you must have a large diameter for the production line, but it was ignored. The result is that the company or this platform didn't or weren't able to produce the production target. It was again a great loss for this company because it invested a lot of money, but because of the bottleneck of the production line, so they can't or they couldn't reach the production rate target. Another company, and actually it is occurring day by day or every day into oil companies that ignoring the positional environment modeling and the rock data and coring activities and so on. Actually, I have a webinar that is called Coring is Not Touring. I think that is very interesting, and also it was conducted with Reservoir Solution Company. Into that webinar, I indicated the importance for reservoir core data for the field development planning. So again, usually we have the depositional environment for some reservoir as sand channel. So to model the distribution, the sand channel, as you can see that it has a sand body, and the sand body is surrounded by shale. So if you don't have proper modeling for the sand channel, so it will lead to have many dry wells because we should drill at the sand channel. So if you don't have a modeling to the direction of sand channel, so you will drill many wells at the background facies, which is shaly facies. At the end, also we have the sand ocean or the sand production problems. If you have a field that is suffering from sand production, you should have or you should acquire core data to have mechanical or geomechanical modeling for your field, because it will help you to design the well drilling azimuth or the well drilling orientation or direction to avoid the sand production or to prevent or to reduce the sand production problem. If you have sand production problem already, so you will need also some geomechanical properties, which is like the unconfined compressive stresses and the TWC and so on, to have estimation for the proper drawdown that you can have without any sand production. If you have the sand production into an offshore field, it can lead to a disaster. It can lead to the blocking of the production pipelines, and it will be a high mess for this company. So again, actually the field development planning is not one-day task. It is continuous task and updated day by day. The reservoir engineer and the reservoir management team will have a data day by day, new data day by day. So they should update the field development plan day by day, or period by period, period by period. Okay, that is just some activities or some suggestions and approaches that can be followed for every stage of a reservoir life. And at the end, our only conclusion, if we have just one conclusion from our today webinar, is to listen to your reservoir. Please don't ignore any piece of data. The smallest piece of data can a high risk for the total project, a high impact of your project cash flow. So it is the period of questions. So if anyone has any question, please drop it into the Zoom chat. I think that we have many questions. So at what point, we have a question, at what point in the life of the project do you advise the using of EOR technologies to optimize recovery from the field? Again, I will say that we have two sides. We have the production side, and on the other side is the economic. Okay, so you will do some simulation runs. Okay, the first case is no applying any EOR activities. The second case is to run the EOR after 1 year. The third case after 3 years, and so on, and see the effect of application of EOR on the production. Then compare that with the economic modeling for each case, and the case that will have the highest net cash flow, you will choose. Okay. Just selecting some questions that relating to the topic. What are the source of data to characterize the aquifer into the early time of field before drilling more wells to optimize the completion and drilling plans in new wells according to the drive mechanism? So at the early time, I will assume that you have limited production data, and actually the main tool to characterize the aquifer is the material balance. Because we don't drill any wells into the aquifer, except that you will drill some wells to inject water. Okay, but I support that into the early life we don't drill injectors. So the data that you can use to characterize the aquifer into the early stage life of production is from analogy. Just assume by the analogy from the nearby fields. How to overcome the limitations of decline curve analysis with research assumptions. Okay, so for one limitations of decline curve analysis that you can't estimate the water production or associated water and gas production. So in that case you can overcome that into the material balance again. The material balance, and of course in simulation. But I'm speaking now about the most simple techniques, which is the material balance. So into the material balance, we will have a modeling, a multi-phase modeling. We will have initial estimation for the relative permeability. Then we will modify the relative permeability by using the historical production data. Okay. We have equation. That equation, for example, the equation of water-oil ratio. The water-oil ratio is equal to the water rate over the oil rate. So if we substitute by Darcy equation, so you will see that you will have relative probability for water over the relative permeability of oil multiplied by constant. Okay, so we have the KRW over the KRO at equal to the water-oil ratio. So if we have a changing water-oil ratio, so we will have a changing ratios for the KRW over the KRO. So that the changing water-oil ratio will be related to changing in saturation of multi-phases, oil and water. So if we have saturation versus different ratios for KRW over KRO, so we can model or we can have pseudo relative permeability that can be used into the prediction of water oil ratio and the gas oil ratio. Okay. For the Excel sheet and PPT, I will send it to Abdullah. I'm not sure if Abdullah is existing or not, but he told me that he has a problem into connection. How can we do economic analysis for tertiary recovery for a certain solvent injection? So if I can imagine, so the solvent injection will have certain cost, will have a certain capex, will have a certain opex. Okay, so the injection of solvent into your reservoir will have impact on the production, will increase the production. So that incremental increase into the production, you will compare it to the cost of injection of solvent. If it covers the cost, the capex and opex for such a project, so it's okay. Okay. If it didn't cover, so don't do that project. Don't do that project. Okay. So thank you all, and I hope that I presented a new information for you, and I hope that you benefited from your time into our lecture today, and thank you all.
فين أمير؟ أنا تعال تحت بطل معاي.
تصبر شوي قسمت.